first skill you're going to need for Thermochem is to be able to identify system and surroundings. So say I have some system, I'm going to want to be able to figure out the change in internal energy. And the problems for this are going to look pretty simple. Generally, you're just going to need to be able to read the problem and then figure out what's coming in and what's going out, and then, take the in and minus the out of the energy. So these ones are just kind of reading problems, and you need to look for like the verbs of the word problem to see like what energy would be coming in. If something's doing work on the system, then that would be coming in. And if the system is doing work on something else, then that would be going out. So you just got to read the problems, and this one will be a lot easier to explain with an example. A system does 753 kilojoules of work and gains 516 kilojoules of heat from the surroundings. What is the change in internal energy of the system? So we have some system, and we have some system, and it's doing 753 kilojoules of work. So it's doing that on the surroundings. The system's doing it, so we know it's losing that much energy. So we know that's going to be negative. We know because they say that it's doing work, it will be losing energy in that sense. And it's gaining 516 kilojoules from the surroundings, so that would be coming into our system. So this one's positive, this one will be negative. So then our change in energy, the change in internal energy of our system, negative 753 plus 516. And I don't have a calculator, but I'm going to guess that's B. Wait, no, oops, that would be A. 700 is a bigger number than 500. Okay, so that would be A. So the skill here is to just be able to pick your system consistently and then figure out the signage. And I've seen this specific problem where you need to have that skill on pretty much every single test. So make sure you can identify system and surroundings. That's the first skill necessary. Okay, now that you can do that, let's add another element of temperature changes. So when we have a temperature change of a system, we can map the heat or the energy changes according to this relationship. Q, the heat transfer, is equal to mass times the specific heat times the change in temperature. So Q equals MC delta T. Q is the heat transfer. Let me write this. Or just heat. M is mass. C is the specific heat. This is a property of your material. And then delta T is just change in temperature. Okay, and then what are the units of these ones? You're going to have joules, grams. This is going to be, well, what is temperature? Temperature is going to be degrees Kelvin. And this one is going to be joules per gram per degree Kelvin for the specific heat. And some problems you're just going to need to recognize that you're going to need to use this equation and plug it in. It should be pretty explicit. The problem should stay, well, let's take a look at a problem. A 514 gram block of aluminum cools from 365 degrees Kelvin to 298 degrees Kelvin. What is the energy change associated with this temperature change from the standpoint of the block of aluminum? So first of all, standpoint of the block of aluminum, that is saying that the block of aluminum is our system. So, aluminum, that should be a lowercase l. Okay, and we know the specific heat. So let's write our equation. Q equals MC delta T. We know the mass. We are looking for energy change, which is going to be Q. And we know the specific heat. That's known. And for temperature, we're given the initial and final. Whenever you're taking a change, you're going to take the final condition minus the initial condition. So delta T is going to be 298 minus 365, which equals negative 67. So then if we plug in what we know, Q equals 514. Let's keep track of the units too. 514 grams times our specific heat is 0.9 joules per gram per degree Kelvin. And then our change in temperature is negative 7 degrees Kelvin. Let's check our units. Grams cancel right there. Degrees Kelvin cancel there. And then we're left with joules, which checks out. So let's put this in our calculator. 514 times 0.9 times negative 67. Q equals negative 30,994.2. And they want the answer in kilojoules. That's in joules. To convert into kilojoules, there is 1,000 joules in 1 kilojoule. So just divide this by 1,000, 30.9942 kilojoules. Okay, so, and let's also intuitively make sure we get the sign right. So it's obviously not C, D, or E. What is the energy change associated with this temperature change from the standpoint of our block of aluminum? So the block of aluminum is our system, and it's cooling down, which means energy is flowing away from our system. It's cooling down. We're losing kinetic energy. We should have a decrease in the energy of our system. So as we calculated, we got negative 31 kilojoules. That's correct. That should probably be a negative number, which is correct. PV work. Okay, let's first take an instance when we have a reaction such as this one, and say we have two isolated constant volume containers. When we undergo this reaction, and we know that this will follow the ideal gas law, or closely at least, it'll follow the relationship. So as we're undergoing this reaction, we are changing from 2 moles of gas into 2 plus 1 mole of gas. So we are increasing our number of moles, and we are not changing our volume. So we know that comparing this first condition into our final state there, we are going to have an increase in pressure. Okay. So now let's consider another instance where instead of having a fixed volume, we have a sort of piston system here where the top arm can move up or down and equalize itself. So, and you'll see this a lot in thermodynamics sophomore year, which will be fun. But there's an atmospheric pressure out here that's exerting a force. We know pressure is force per unit area. It's exerting a force. And if we increase the pressure inside this tank, as we do, this arm can move up to increase the volume and then re-equalize the pressure. So when we undergo this reaction and then increase from 2 moles of gas into 2 plus 1 moles of gas, or 3, in our vessel, there's going to be this increase in volume. Volume will increase if pressure is held constant. And we also know that there is a work change associated with this volume change, according to work equals P delta V. Negative. So when we have a reaction like this, in this condition, where we're increasing the number of moles or decreasing, there's going to be, and our pressure is held constant, there's going to be a consequential change in volume of our system. And because we're changing this volume, there's going to be a work change associated with it, and there's going to be energy changes. So let's take a look at how they're going to test you on this. For the following reactions at constant pressure, which is that last situation we just described, determine in which reaction no work is performed on or by the system. Yikes. Okay. So they want the condition where no work is performed. So we know work equals P delta V. They want the condition where work equals 0. So for this condition, we're going to need a 0 change in volume. Which case is that going to be? That's going to be when pressure is equalized, there will be no change in volume, when the number of moles of the reactants equals the number of moles of the products. So let's just look at our reactions here and see which ones that's the case. So for A, we have 3 moles of reactants on the left turning into 3 moles on the right. So it looks like that one's probably going to be our answer, but let's check the other ones too, just to make sure. For B, we have 3 moles turning into 2 moles, so that there, the volume would decrease. For C, we have 2 moles turning into 4 moles. The volume would increase there, and there'd be a change in energy. For D, we have 2 moles turning into 1 mole, and then for E, we have 4 moles turning into 2. So for these 4, there's a change in number of moles of the system, which would then give us a change in volume and a work done. So the work would not be 0. So our answer choice here is going to be A. Enthalpy changes from reactions. So when we have reactions, we can have enthalpy changes associated with them. They can be endothermic or exothermic. Endothermic is when it takes energy to form the products, and you're putting energy into the products. This is going to be represented by a positive delta H value, and if it's a negative delta H value, then it's going to be exothermic. Oh, it's bolder. Okay. Exothermic. Exothermic reactions are going to release heat. You can think about like combustion in a car, very exothermic, very explosive. And that's going to be signified by a negative delta H. With these reactions, and also another way to visualize it perhaps, that's how they're always going to write it. They'll always have delta H on the product side and then like equals 100. An endothermic reaction would be like 100 kilojoules per mole plus, something like that. If it was exothermic, the energy would be on the right-hand side. Because as you'd be forming it, the energy would be with the products. So, oh, I erased my arrow. Okay. When we're also doing these reactions, we can add up these energy changes, these enthalpies, associate per 1 mole. So as 1 mole of equivalent would react, we would get 100 kilojoules of, it's endothermic, so it would require 100 kilojoules to form the product. So let's say this, to make this maybe perhaps a little bit simpler, let's say this is exothermic. So we're releasing heat. If we formed 1 mole of oxygen, then we would release 100 kilojoules of energy. If we had 2 moles of oxygen formed, we would release 200 kilojoules of energy. So they go in the stoichiometric ratios, similar to what we've seen in other problems. And they can also ask you to combine them. So if we had 2 reactions, even though the 2 reactions I have here are the same, you could add these up. So let's say this one is also negative 100. I could add these reactions together, and then I could say 4H2O2 is 4H2O plus 2O2. And then I could add these delta H's to yield negative 200 kilojoules. Obviously here, my example is the same reaction. But if they were different, you could do something similar, which is generally what they're going to ask you. So let's take a look at that problem. Calculate the delta H for this reaction. And then they give you a overall reaction, and then they give you 2 half reactions. So we need to combine these 2 reactions in a way, and then follow how these delta H's are going to change, and then add them up. So let's take a look here. First thing I noticed, we have calcium on the reactants, and calcium only shows up in this first equation on the reactants. And also it has a stoichiometric coefficient of 1. It also has a 1 there. So, however we're going to combine these 2 equations, we're probably just going to add 1 of the first reaction. If we take a look, and same deal with oxygen, that's a half. If we take a look now at the calcium tri... what is that? Calcium... Why am I blanking? Calcium carbon trioxide. That is, they want that as a product, but the second equation here has it as a reactant. So what we can do is we can flip this. We can say that this plus carbon dioxide forms this molecule. And then what I'm gonna do is flip the delta H. So now it's negative 178.3. And this is no longer useful to us. Now, if I simply add up this first equation with the second equation, I should get the overall equation. So then I would have calcium plus half O2 plus, wait, okay, this 2 is not a stoic ratio. Oops. Plus CO2 turns into CaCO3 plus CaO. These are on both sides, so they would go away. And then I can also add this number to that number. Let's see what that gives me. So then my overall delta H is going to become negative 813. A lot of these type of problems show up a lot on the test. So make sure here the skill is that you can combine half reactions to get to the full desired reaction, and then know that you can combine these delta H's in the similar way. So if for example, I also could have maybe multiplied this by 2 if that was necessary, and then I could have multiplied this answer by 2, because essentially what I did is I times it by -1. So you can perform whatever algebraic operations you want to get the final reaction. So here I got D, negative 813. Next topic, ideal gas law. So we know the ideal gas law is PV equals nRT. This is a general relationship between the thermodynamic properties. R is a constant that they're going to give you at the bottom of the test. Generally, it's going to be 0.08206 liters times atmospheres over moles Kelvin. It's really important that you keep track of the units. I've seen a lot of times that they will give you a problem that uses milliliters, but the R value they give you is liters. So how would you convert this? You can just use, 1 liter. In 1 liter, there's 1,000 milliliters. And then, liters cancel, and then you're left with milliliters. So make sure you use the right R value. That could be very important. That's what is this, liters? Okay, I think that's the first thing. We also know that the total pressure of a system can equal the partial pressure of different species. So say we had like species A, species B. You can add up the partial pressures and their contributions to get a total pressure. So say, for instance, I had some system with species green and blue and red. I could do the ideal gas law for green, blue, and red and then add them up. I could do like 3 different ideal gas laws. Okay, that one's like the blue species. I could do another ideal gas law for the green species, and then like the red. And then I would throw all of these into here, and then I could add them up to get a pressure total. And this is a format they might ask a lot. This is one of the ones where they might give you a question that really you just need to know the ideal gas law, but you need to know that you could break up the species and add them up like this. So let's take a look at an example. A mixture of 0.15 moles of hydrogen gas and 0.125 moles of oxygen gas is contained in a vessel with a volume of 30 milliliters. If the atmospheric temperature is 298 Kelvin, what is the total pressure in the balloon? We have a balloon, we have hydrogen gas, and we have oxygen gas. So we have two species. We know the temperature. So let's take a look. PV equals nRT. We are looking for pressure. We know the volume. That's known. We know the number of moles of each species. That's known. R would be given to us, so that's known, and we are given the temperature. So let's solve for each species. Let's do the hydrogen gas first. So, and also if we solve for P, you get P equals nRT over V. Just divide over the V. So let's get the partial pressure of H2. This is going to equal N, which is 0.15 mole, R, which we know is 0.08206 liters atmosphere over mole Kelvin. But we want this in milliliters. Let me erase that. They have this in milliliters, so let's not get tripped up. Let's use our conversion factor. We know in 1 liter there is 1,000 milliliters. So let's times this by 1,000, and you get 82 milliliters, 82.06 milliliters atmosphere over mole Kelvin. So we can put that in. My balloon's a little big. I'm just going to erase it. Okay. Milliliters atmosphere moles times degrees Kelvin. Okay. And then we have times it by the temperature, which is 298 Kelvin, divided by the volume, 30 milliliters. Okay, let's check our units too. Moles cancels with moles. All fine. Wonderful. Moles cancel with moles, degrees Kelvin, milliliters will cancel, and then we're just left with atmospheres, which is what we want. Also, it's the pressure unit. The answers have it in, so wonderful. So the partial pressure of H2, let's plug this into our calculator, 0.15 times 82.06 times 298 divided by 30, 122.26 atmospheres. Okay, let's see now what the partial pressure of O2 is going to be. We can just start plugging right in right away because we kind of already did it once. 0.125 moles of O2. Same R value, it's a constant, it shouldn't change. Milliliters per atmosphere, or milliliters times atmosphere per mole per degree Kelvin. Same temperature for the system, and it's occupying the same volume. And the units cancel in exactly the same way. 0.125 times 82.06 times 298 divided by 30. So the partial pressure of O2 equals 101.89 atmospheres. And we know that P total, switch colors, do blue. P total equals the partial pressure of H2 plus the partial pressure of O2, which is just going to be 122 plus 101. So 122.26 plus 101.89, 224.15, which is A. Phase changes. So this topic I have not seen explicitly on a test, but that definitely does not mean it could not be in the future. And I'd feel bad if I didn't at least say it. So we know when we have reactions, say, A turns into C plus B, you can have an enthalpy change associated with this. Well, you can also have an enthalpy change associated with, it's supposed to be an A, with a phase change. So say I have solid A and it is turning into liquid A. There would be a delta H of fusion associated with that. AKA, say you have ice and you're melting it. There's an energy change associated there. And you can have phase changes like this, where as you heat a species, as you add more heat, the temperature will change like this. These slopes are where you're just heating up your species. These are going to follow your Q equals MC delta T. These areas where they're flat and you're not changing the temperature, these are where all your heat is going to be going into these phase changes. So this first one would be delta H of fusion. And then once you're done, once your species is entirely melted or frozen, you can also go the other way. Say it's entirely melted, then you'd heat it up again. This would also be Q equals MC delta T. Your C would be different though. C's, at least in Chem 115, generally only change with phase. They do also change with temperature, but that's not too much of an issue in this class. So along these slopes, we're following the Q equals MC delta T. And then you have another phase change. This is going to be delta H vaporization. And then we're going to heat again. I don't have a practice problem for this one. But theoretically, they could say, how much heat does it take to go from this point to, up to this point? And then you could do this temperature change according to this equation, add it to the energy change according to this equation, and then you'd be over here, and then do the energy change for that point. So that's Thermochem in a nutshell.